Today we're going to look at the first of two universal gates, the NAND gate, which also happens to be the first IC ever created, was the NAND IC. And after today, hopefully you'll understand a little bit more about why that might be. All right, so we're going to learn about the basic function of a NAND gate and how it can replace an AND OR and the inverter gate. How we can re-implement AOI logic with NAND gates. And the last thing is basically that when we replace NANDs or AOI with NANDs, we do something wonderful. There's three key things that I always talk about with my students in digital electronics. Three things that are very important to the companies that make this. Okay, money, obviously. Speed is always very important when you're talking about computers and electronics. And power usage, because we don't want it to use too much power, especially if it's running on a battery. Okay, reducing the number of gates and the number of ICs, which this can do, will take care of all three of those. All right. So this is what an AND gate looks like. It's an AND followed by an inversion. Okay, so you have X and Y go in, becomes X and Y, the whole thing inverted. And according to De Morgan's theorem, we break the line, change, change the sign, and we end up with not X or not Y. If you look at the truth table here, it is just literally the inversion of an AND gate. So on the output Z, everything is the opposite of an AND gate. Instead of 0, 0, 0, 1, we have 0, or 1, 1, 1, 0 on our output column. All right, so it's an inversion of an AND. So how do we replace the inverter gate with a NAND gate? By basically taking the variable, running into both the inputs there, as you can see occurring here. Okay, so we have X, and it's going into both the inputs. When that happens, we end up with X and X. That's before it goes through the bubble. And then it goes through the bubble and becomes not X. Okay, because X and X, remember your Boolean logic rules, X and X becomes X. And goes through the inverter X, which so basically all it did to X was invert it here. All right, so how do we make an AND gate? Well, an AND gate is an AND inverted. So if we follow it by another inversion, that'll cancel out the first one. So here we have a NAND gate going in. So it's an AND followed by an inversion. So that would be X and Y inverted. And then if we run that into another inverter, remember this was our equivalent NAND gate inversion, okay, we get not X and Y, which cancels out and just leaves me X and Y. So we have an AND gate. All right, now we're going to get really crazy. We're going to take a NAND and we're going to change it into an OR gate. Okay, well, we're going to make an OR gate out of NAND, so that would be a better way of saying that. So basically we have our two inverters here. Okay, X inverted becomes not X. Y inverted becomes not Y. So that's fairly obvious. We run that into a NAND gate, another one. Okay, and we get not X, not Y, and that whole thing inverted. Well, break the line, change the sign using De Morgan's theorem. We get not X or not Y. And those double negatives cancel out, or double inversions, and we're left with X or Y, which is an OR gate, very simply. Okay, and if we look at the truth table, it's equivalent to an OR gate. To summarize, here is your table of equivalents. So an AND gate looks like this, an OR gate looks like this, and an inverter is this. All right, so the inverter is just running both the inputs the same, and that will invert whatever that input is. An OR gate is this tier of three, basically two inverters followed by a NAND gate. And then an AND gate is a NAND gate followed by an inversion, which basically creates a double negative there and cancels out the inversion. So here are the steps for taking an AOI circuit and re-implementing it with NAND gates. All right, so step one is first make your AOI circuit. Step two is figure out what the equivalent NAND gate would be for each one of the AND, OR, and inverters in your circuit. Okay, next, redraw the circuit with those replacements. Then fourth, we haven't gotten to this yet, so it'll come back in a minute here, so just stick with me. But cancel out any double inversions, and finally redraw the circuit one more time. Let's not be lazy and just leave it crossed out. Sorry for the ding. All right, so here's a very simple AOI circuit drawn out. Nothing too complicated here. We're going to take each one of those gates and we're going to find the equivalent for them in the universal NAND gates. Okay, so we found out the equivalent of the inverter. The equivalent of both ANDs is this. And the equivalent of the OR is that. And of course, we're just going to take them and replace them. Okay, nothing too complicated. So this is what it looks like once we've replaced them. Okay, now we're going to look for those double inversions. So what I'm talking about is, remember, this is what the inverter gate looks like when it's a NAND gate. Both those outputs, or sorry, both the inputs are connected together. Okay, and see how both the inputs are connected together here? So that's an inversion followed by an inversion. Same thing here, inversion followed by an inversion. Okay, well, when we double invert, we basically do nothing. Okay, so those can go away. Okay, so we're going to X those out, and we're going to redraw the circuit. Boom. Doesn't that look beautiful? I think it does. Okay, and guess how many ICs we're down to? Just one now. All right? So, this is just showing you it's equivalent to what we started with, which is B and not C, and or A and C. Now, if we just look at it, this is a gate analysis here, and we can look and see when we started out with the original AOI over here, we were using 3 ICs because we had to use an inverter, an AND, and an OR. So we had a 74LS04, 74LS08, and a 74LS32, 3 ICs. Okay, so same thing though, we have 3 gates here, so I guess we're not really saving on speed or well, speed mainly. But look, since these 4 all occur on the same IC, I'm only using 1 IC. So I am probably saving a little tiny bit on power usage, and I am saving money from cutting it down from 3 ICs to 1 IC here. All right? So always important to your boss to save them money. And like I said, in digital electronics, speed and power are also important. Okay? So at this point, it's your turn to try. If you don't understand what's going on, please, please, please ask your instructor. All right, I'm out of here.